All right. So now that we've talked a bit about making formula for sequences, let's talk about something else we really want to do with sequences, which is take the limit of a sequence. Right? When we're taking the limit of a sequence, we're asking what value are the terms in this sequence approaching? Yeah, that's right. All right. So how do we do that? All right. Turns out it's actually nearly identical to how we take limits of functions. Right? So if it, let's say, if the limit of a sequence is L, we say the sequence converges to L, right? Now, when we're taking limits of a sequence, we're basically going to do the same thing we normally do, right? Actually, sorry, let me give you one more term here, right? So if the limit of a sequence exists, we'll say if the limit doesn't exist, the sequence diverges. Right? So to compute the limit of a sequence, what we do is we essentially need an explicit formula. Right? It can be done without an explicit formula, but it's a lot easier to do if you have one. Right? So given an explicit formula, right? So an equals, really an explicit formula is really just a function of n, if you think about it, right? Think about all these examples back here. You know, we're saying, all right, here's some function of n. Here's some function of n. That's all we're really doing. Right? So given an explicit formula, right, the limit of a sequence, which we would write as limit as n goes to infinity of an, this limit here is just the limit as n goes to infinity of f of n. Now, technically speaking, the domain of this function f is just, integers like 0, 1, 2, 3, 4, so on. But it turns out we can just think of this as a normal real-valued function, right, where we can plug in any number. And so we can just apply the same kind of techniques we normally would. Right? So, for example, let's look at the sequence minus 1 to the n over n squared plus 1. Right? Let's look at something like this. All right? So what can we do here? So here, f of n is equal to negative 1 to the n over n squared plus 1. Right? So we can try and see, what's going on here. Let's switch over to Mathematica and look at this thing graphically. Right? It'll also give us a chance to talk about how graphs of sequences look. Right? So here, right, here we have, this is our sequence up here. Right? This is the an term. So what we're going to do is we're going to make a function. All right, a of n, and it's going to be our an term. Our term, right? Now, when we're graphing a sequence is a list of numbers. It's not a continuous function. So what we can do is use something called discrete plot. And here I'm going to graph the first 10 terms of the sequence. Right? And what you can see here is this thing sort of bounces back and forth. Goes up here, down, Looks like the negative or the one term is cut off a little bit. Let's try and fix that. Let's see, full. There we go. Got cut off a little bit. All right. So when n equals 1, we're down here at negative 1/2, and then we go up and then down and So down here, up, down, up, down. So we're kind of bouncing back and forth. So see if you can find like a pattern in this sequence, right? If we look at it here, it's bouncing back and forth, but it's leveling out around 0 here. So it makes sense to say that the limit of this sequence is probably 0. And we can even look at this, in a table here and look at the actual values of the sequence. So here's the n values over here. Here's the output values. All right. Could also, if we wanted, say, make this numerical if you wanted. So you can look at it in terms of decimals and see, what the pattern seems to be doing. It's kind of up to you how you want to look at these. All right. But what you can see here is, all right, these fractions, they keep flip-flopping between positive and negative, but regardless, they're always getting closer to 0. All right? So how can we actually figure that out? One thing we can do is try and figure out a function whose graph is this, whose graph passes through all these points. So let's look back here. There's a couple ways we can do that. But an easier way to sort of think about finding sequences, especially this negative 1 to the n thing, can often be a bit weird to deal with. So what we can do here is say, okay, so here's our an. A fact that's true is that if limit as n goes to infinity of the absolute value of an equals 0, right, then the limit without the absolute value is also 0. This is a true fact right here. Right? So what that's essentially going to allow us to do is ignore this negative 1 to the n. So let's take the limit as n goes to infinity of the absolute value of this. Right? So this is limit as n goes to infinity of 1 over n squared plus 1. And if you think back to how we compute limits, well, we can see that this is 0. So that implies that the limit as n goes to infinity of our sequence that we're actually interested in is 0. Right? Now, why does it work for the absolute value equals 0, or the limit of the absolute value equals 0, then the original one must go to 0? Because what we're doing there is absolute value is telling you how far away from the x-axis your points are. And if your points have to keep getting closer to the x-axis, it doesn't matter what side they're on, they've got to go to 0. Right? So that's one way to look at this. Right? Or that's one example here. Now, let's look at another example here. Actually, I'm just going to do this one in Mathematica. Right. So let's look in Mathematica here. I want to show you how to plot a recurrence relation. Right. So let's say we have a sequence. Where's my mouse cursor? It's never in the spot where I want it to be. It gets captured in the wrong spot. Anyway, so let's say we have this sequence here with this recurrence relation right here. All right. So an plus 1 equals 3 minus 2an, and our first term is 2. So how do we program something like that and look at the graph of it? Right? So what we're going to do is clear a and n as usual. Right? I'm going to define the first term of my sequence to be 2. So a1 is equal to 2 right here. Okay? And then I'm going to write a do loop. This is kind of a do while. So here we're saying, define an plus 1 to be 3 minus 2an, where n goes from 1 to 20. Right? So we already have a1. When we plug in n equals 1 here, we're going to say a2 is 3 minus 2a1. And this loop here will continue to define all your terms. And this actually defines you all the way up to a21, because we have this up to 20 here. Oops. Right here. Like I said, my cursor never captures in the right spot. I don't understand why. But anyway, so let's go ahead and see what this plot looks like. So let's run that. All right, so we're looking at a sequence like this now. Right? So here, we have some dots that aren't moving very much, and then they start bouncing up and down really quickly. And again, we can even say, plot range all here to get everything. Oops, not all. Full, sorry. Oh. I guess these values get quite a bit too big. All right. Yeah. So, all right, I guess they're getting too big for us here. So if we look at this, though, these values are bouncing back and forth. You can see these little faint lines here. These little faint lines. These lines draw from the axis to the actual value of the sequence. And here you can see they just keep going out. And if you look at this, this isn't settling on some number here. It keeps bouncing back and forth. And what it does is it actually gets further and further away. Let me try this. Plot range. Let's try this. See if we can get... Oh, I'm putting this in the wrong spot and not even paying attention. This goes here. I don't know why I was putting it in the in the do loop. Yeah, so if we look at this here, right, these values keep getting further and further apart. So this is an example of a sequence that does not converge, right? Because the values of the sequence keep continuing to grow. All right. And we can verify that by looking at it numerically, right? So here we can see what's going on, right? If we just keep looking at these are getting larger and larger, and they keep flipping back and forth in sign. So we can't even say like the limit is infinity or the limit is negative infinity, because it keeps bouncing back and forth between positive and negative. So the limit just simply doesn't exist. All right, so hopefully that makes sense there. And see you in the next video.